Hello guys, welcome to our YouTube channel. Today in this video I am going to tell you about the op-amps, that is the offset voltage and the current of the op-amps operational amplifier. First I am going to tell you about the output offset voltage, that is the voltage present at the output without any input being applied is called as the output offset voltage. That which means even if the input is not applied to the operational amplifier, both the terminals are inverting and non-inverting terminals are grounded, there would be small voltage seen at the output of the operational amplifier. This voltage is termed as the output offset voltage. Now the question is, how or why is this small voltage present at the output? What is operational amplifier? It's nothing but a differential amplifier which consists of transistor. It consists of two transistors which doesn't have the same characteristics, which will have the different characteristics. Different characteristics in the sense they will have difference in the collector current, different collector current. So this difference causes some small differential output which gets amplified in the further stages. So that's the reason there will be some voltage present at the output called as the offset voltage. Next, let us see into the input offset voltage, which is if both inputs are grounded, ideally the output must be 0. But if to nullify this, what we are doing is, if the output is, say, example 3 millivolt, we are applying the negative of that. That is to nullify the voltage present or at the output, that is small voltage. We are giving the negative of the same voltage to either one of the two inputs. This voltage is termed as the input offset voltage. It's about the input offset voltage. Next is we are going to see the input offset current. It is nothing but the algebraic difference between the currents flowing into the inverting and the non-inverting terminal of the op-amp is referred to as the input offset current. Here IB1 and IB2 represents the current flowing into the inverting and non-inverting terminal. The difference between them is current is given as IB1 minus IB2. That is the base currents of the first differential amplifier stage. And even if both the transistors are identical, it is not possible to have IB1 and IB2 exactly equal to each other because of the internal imbalance that is present between the two inputs. So they will be different. So that difference is termed as input offset current. Next, we are going to see about the input bias current. It is nothing but the average of the currents that flow into the inverting and non-inverting terminal of the op-amp. Average in the sense we have to add these two currents, IB1 and IB2, divided by 2. It represents the input bias current. That's average of the base currents. Next, we are going to discuss is the common mode. So what is common mode? When the same input voltage is applied to both the input terminals of the op-amp, the op-amp is said to be in the common mode configurations. Let me represent VOCM as the common mode output and VCM as the common mode input. Then the common mode voltage gain, which is represented as the ACM, that it will be equal to the ratio of VOCM divided by VCM, that is the common mode output by common mode input. Ideally, op-amp amplifies only differential input voltage, but due to imperfection within the practical op-amp, some voltage will appear at the output. Next, we are going to see the common mode rejection ratio. We have already seen how the common mode voltage gain is seen, that is the ratio between the common mode output by common mode input. The CMRR, that is common mode rejection ratio, is nothing but the ratio of the differential gain AD and to the common mode rejection gain, common mode gain, that is ACM, which is represented as 20 log AD by ACM. Generally, this CMRR is expressed in decibels dB. For 741 IC, that is operational amplifier, the CMRR is 90 decibels. Also be expressed as the ratio of the change in the input offset voltage to the total change in the VCM voltage. VCM in the sense the common mode input voltage. So that's about the CMRR. Next is the supply voltage rejection ratio, that is the change in an op-amp's input offset voltage, that is VIO, caused by the variation in the supply voltage is called as the supply voltage rejection ratio. It's given as the delta I VIO divided by delta V, where delta VIO is the change in the input offset voltage and delta V is the change in the power supply, that is the supply power. That's about the SVRR. Next is the thermal drift. As the name indicates, thermal means the change due to temperature. Ideally, the parameters like VIO, IB, IO, that is input offsets, are constant for input, but practically they vary with the change in temperature, change in supply voltage VCC and VEE, and also with the time. The average rate of change in the input offset voltage per change in temperature is called as thermal voltage drift. It is expressed as delta VIO divided by delta T, which is expressed in microvolt per degree Celsius. Next is, in the similar way also we can define the thermal current drift, that is the change in the input offset current per unit change in temperature, and also the thermal drift in input bias current, that is delta IB by delta T, change in temperature. This is all about the thermal drift. Next, I am going to say about the slew rate. Slew rate is defined as the maximum rate of change of the output voltage per unit time. That is, let this be the input and the output will be something like this. That is, it is defined as the maximum rate of change of output voltage per unit time, that is dV by dt per unit time. It indicates how rapidly the output of an op-amp can change in response to the change in the input frequency. Thank you for watching.